So we're assuming we're using a 172 model November. So let's talk about the power plant. So let's talk about the engine. So the engine in the Cessna 172 that we have, there's some key words that you need to know.
I'm gonna take note as a student, okay?
Okay. So there's some key words that you're gonna need to know to be able to recite on the checkride as a private student. As a commercial student, you're gonna really need to understand what these things mean. So you in the Cessna 172 model November have a Lycoming. The Lycoming is the brand of engine. It's actually, funny enough, it's made by Textron. Textron is the company that owns Cessna. So the company that owns Cessna and the company that owns the engine inside of the Cessna are actually the same parent company.
Wow.
But your engine is a Lycoming O as in Oscar 320. The O means that the cylinders are horizontally opposed, and I'll explain what that means in a second. And the 320 means that it's 320 inches of cubic displacement. So that's the size of the engine, and it creates 160 horsepower at 2,700 revolutions per minute of the engine. So it's an O320 engine. So horizontally opposed means that you've got 4 cylinders, and I've got a picture of cylinders on the screen here, but those cylinders are rather than you've heard of a V6 or a V8, the cylinders in your airplane are not in a V. They are opposed, horizontally opposed from each other. 2 cylinders on one side, 2 cylinders on the other side, opposed.
Other side of what?
On the other side of this, so if you think of the engine casing, the engine block, one set of cylinders stick out one side, one set of cylinders stick out the other side. So like the port and the starboard side of the aircraft.
Okay, port is right.
Port is left.
Left, okay.
So the engine is air-cooled, meaning that it's dependent, it's not water-cooled, it's not necessarily the entire engine oil-cooled, it's air-cooled. It's naturally aspirated, meaning that some aircraft engines use compressed air in the induction cycle, which I'll explain what that means in a second, by way of a turbocharger or a supercharger to really, really compress that air. This airplane does not. It breathes normal atmospheric air, just like you and me. And that's why as we climb in this aircraft, you produce less and less power as you get higher and higher. That air is thinner. You've got less air molecules. And so the engine performance subsides as you climb. It's direct drive, meaning that the propeller is connected directly to the crankshaft. And again, it's 320 cubic inches. So that's the airplane, the engine that you have in this airplane. I'd like to talk about how an engine works in general. And so I've got some cylinders on the screen here, a graphic. You may have heard the old adage that a 4-stroke engine has 4 strokes. It has 4 phases that it goes through. You've heard of suck, squeeze, bang, blow. So the idea is that represents the 4 stages that a cylinder can go through. So you've got the idea is a cylinder is, just think of it like a soda can with a plunger inside of it, a piston that has a seal inside of that. And so if you imagine here, I don't know if I can draw on, no, I can't draw on the screen as I've, maybe.
But I'm kind of getting the hang that this square part, that's actually the plunger.
So yeah, but I want to be able to explain it.
Okay.
All right, so if I've got a piston here, The idea is that you've got this plunger right here where I'm circling in red, and you've got this
Okay.
arm, this connecting rod that is connected to the crankshaft that's spinning. And these pistons are all interconnected in the 4 cylinders. So as one piston is pulling down or is coming down and making a bigger space, the next connecting rod is pushing the piston up and is making a smaller space inside of the cylinder. So as that connecting rod draws the piston down, that's the intake phase. So what's happening is fuel and air is getting sucked or put into the cylinder, a fuel to air mixture that we control with both the throttle controlling how much stuff goes in, and the mixture controls the fuel to air ratio. We're shoving or we're sucking the fuel and air into the cylinder in the intake stage. The next stage is compression. So once we've drawn all of that in, we compress it down, and that piston goes back up. The connecting rod pushes it back up, and that fuel to air mixture compresses. The next phase is the magneto fires a spark through the spark plug via an electricity current that the magneto is producing. That spark ignites the fuel to air mixture. We're here now in the 3rd stroke, and that shoves the piston down fast. That piston, again, that's the bang. That's the bang. So the piston is connected to the connecting rod, and that drives the crankshaft. So this is the power stroke. The power stroke is the one that's actually making all 4 of these pistons move via the connecting rod and is turning that crankshaft, and ultimately is giving power to the propeller. And then after the bang, after the ignition, after the power, then that connecting rod pulls the piston back up, and that's the exhaust phase here, number 4. The exhaust phase is pushing that spent fuel to air mixture that's now exploded out through the exhaust manifold and ultimately out of the pipes of exhaust on your airplane. It's important to realize that each of these cylinders goes through all 4 of those phases or all 4 of those strokes, but at different times. As one cylinder is intaking, right, it's opening the cylinder. There's another cylinder that is banging, right, that's creating power, also opening the cylinder, but with power. Oh crap, there's my machine is getting patched here. Can I close this? So the intake is creating space in the cylinder. The power stroke is creating space in the cylinder. Connecting rod ties it all together. So as those 2 cylinders are opening, the compression cylinder is closing and the exhaust cylinder is closing. So all 4 strokes, suck, squeeze, bang, blow, intake, compression, power, and exhaust. Again, all of those connecting rods are tied to one crankshaft, and then that crankshaft is turning, and that crankshaft is connected to the propeller, and ultimately that's what's turning the propeller. Yes.
Do we have any depiction of that connecting rod? I see it says crankshaft over here. So I kind of like, I can imagine that there is a rod going between those crankshafts, basically.
Yeah, so the connecting rod is right here. If you see my yellow.
Yes.
The connecting rod is that. It's literally the thing that connects the piston with the crankshaft.
Do you mind if I kind of like repeat what I heard?
Sure.
So basically what you're saying is that we have 4 of those cylinders, and they are all connected. And there are those 4 phases. And basically what's happening is that fuel and air get mixed, and they get ignited, and everything is connected actually to a propeller. So this whole thing spins, and every stage is actually 1 cylinder at a time. So at all time, there is at least 1 cylinder that's banging, 1 cylinder that's exhausting. So it's kind of like something like almost like a clock, some kind of a mechanism which is perfectly synced, basically.
Yeah,
right?
that's right. There's a synchronization via the crankshaft between the 4 cylinders. That's
Okay.
correct.
Okay.
And this is, by the way, how really any engine works. Your engine inside of your car works the same as this. But again, it's important to understand how this works in an airplane.
Okay.
So moving on with the power plant. So there are a couple other things that you need to be able to understand with this power plant. So I mentioned the magnetos. So a lot of students will ask, so what happens if the battery falls out of our airplane? What happens if the battery dies? What happens if everything shuts off? Does the airplane fall out of the sky? The answer is no, because the magnetos are connected to the engine spinning, and the engine spinning also spins the magnetos, which is basically a magnet with a coil stack. It's a mini generator creating current, and that magneto then sends the electrical pulse to the spark plug that creates spark. So there is no part of the engine system that requires the electrical system to run. Now, you do need a battery to turn the engine over or to start the airplane. The starter needs a kick to turn the propeller. But once it's started, the engine system, the power plant system, is a beautifully self-contained system that does not require any external power. So the magnetos, which there's 2 magnetos firing 4 spark plugs each, 1 magneto for one side of the cylinder, 1 magneto for the other side of the cylinder. Really, for redundancy, 1 magneto could fail, 1 spark plug could fail. The engine might run a little bit rough, but the engine isn't going to shut down when one thing fails. So that's the idea of a magneto, again, at a private level. Is it's a little generator creating its own power driven by the engine itself. So the magneto creates the electricity to fire the spark plug that creates the power stroke in the engine that drives the crankshaft that is connected back to the magneto. So it's a perfect ecosystem, if you will. So that's the idea of the dual magneto, dual ignition. There's a couple situations that you need to be aware of in a power plant that can cause a loss of power. Really 2 things: detonation. Yes.
Are the magnetos kind of like what I saw in like a World War I movie, when they're actually able to just do the prop, and they didn't have batteries back then? So is that the same mechanism? You don't really need a battery. You can actually, like, if you were to push down on the propeller.
Sure. Yeah. If you were to put, if you were to have fuel in one of the cylinders, and you had the magnetos ungrounded, so if your key was in and turned to one or both, and you were to apply power to the propeller via your hand, if you were to hand prop the propeller and get it started to turn, that's going to turn the crankshaft. The crankshaft is going to turn the magneto. The magneto, again, it's a coil stack with a magnet, is going to turn the magnet. It's going to produce power. It's going to fire the spark plugs. And again, as long as there's fuel and air inside of there, it will actually start the engine. Yes.
Okay. Okay.
So two conditions that we need to be aware of that are bad for the engine: pre-ignition and detonation. And at a very simple level, because I do want to move past the power plant and on to some other systems. But detonation, the idea of detonation is that fuel, like the name says, it detonates instead of exploding cleanly and uniformly. So a lot of times detonation will be caused by using improper fuel, the wrong octane, if you will. So in your car, a lot of times we talk about pinging, this pinging notion. If your BMW takes 92 octane and you put in 87 octane, the idea of detonation is that you don't have this really clear, complete burn to the cylinder. Pre-ignition is when you've got a hot area inside of the cylinder, and the cylinder explodes under pressure prior to the spark plug firing. So pre-ignition, just like it says, it's causing the power stroke to happen before it's ready. And again, that is if you compress fuel and air down, and if it's really, really hot, you can have a pre-ignition condition. So that's why we like to look at our cylinder head temps, and if those cylinder head temps get hot enough, we can actually create a condition where the power stroke fires before the spark plug fires. And as you might imagine, because these are all interconnected, that screws things up. You have a partial loss of power. So that's really the power plant. I guess the other thing that I would probably talk about, I probably wouldn't bring this up on the check ride, but one thing you might get into is, okay, is the fuel system, is this a fuel injected engine, or is this a carbureted engine? Well, if you remember when I started out, I said this is a Lycoming O 320 engine. The O means the cylinders are horizontally opposed. You can also have a Lycoming IO 320 engine. The I means that it's fuel injected, meaning you have a little gun that shoots fuel into the cylinder at a kind of a perfectly timed interval. There are pluses and minuses to fuel injection, but your airplane is carbureted. And carburation is maybe a little bit older, but it's foolproof. There's very little moving parts. There are some things that we need to be aware of, like carb ice, the venturi getting a little bit too cold and freezing. But for the most part, carburetors are very, very reliable. I've got a picture of a carburetor here on the screen to explain this at a very, very high, very, very quick level, very private level. The idea here, and I'm gonna take a screenshot so I can draw on it here. So the idea of the carburetor, I guess I can't zoom in there. The idea of the carburetor is you've got a mixture needle. First of all, this is the mixture needle in red. I'm drawing it here. So the mixture knob, the red knob, is directly connected to this mixture needle. And
falling behind a little bit. Can you just tell me what does this do in general?
So this is the carburetor. It introduces fuel and air into the throttle, into cylinders.
Okay. Okay.
So,
and this valve kind of put that kind of like it puts it in and out, right? Like you close this valve.
So let me just explain the whole system. So you've got fuel that's sitting in this fuel reservoir here. The fuel comes into the fuel reservoir as the fuel goes down in level. This float goes up and it goes down and it opens up a valve right here that allows fuel in. In the Cessna 172, you've got a gravity-fed fuel system. So the fuel, as that valve opens, the ball goes, as the ball goes down, the valve opens and you dump fuel into this reservoir. Then, like I was explaining, the mixture knob, the mixture needle is directly connected to this system right here. As you increase the mixture, it backs the needle out of this bottom area, which is very hard to see me draw here.
Okay.
But fuel then goes through this little line here and into this nozzle. The discharge nozzle. This, you can see the throat of the Venturi is curved. If you, I'm going to switch to yellow right here.
Yes.
These curves, just like a wing, where the sides of the Venturi are curved, the air has to speed up to get over that area. As air speeds up, it creates an area of low pressure, just like a wing. It's how lift is created. And that low pressure draws fuel then from the inlet. So you've got air, you've got a constant amount of air coming in here, right here. And then you're introducing fuel via the discharge nozzle, and you're controlling how much fuel is coming there by either backing out the needle right here, or putting the needle in more. So as you lean the mixture, you're dropping the needle in, and that's clogging or closing this little teeny tiny valve on the bottom. So that's the fuel to air mixture. This thing, this butterfly valve, this silver thing, that's your throttle. So as you push the throttle in, that black knob in the Cessna 172, it twists this valve, this silver thing, to the open position. And then you can see if it's perpendicular to the Venturi, all of that stuff that's in the Venturi, however much air and however much fuel, goes then into the engine. And that's very simply how a carburetor works. So the carburetor is controlling the fuel to air mixture, and via the throttle valve, it's controlling how much of the fuel to air mixture goes into the engine, goes into the cylinders. Does that make sense?
I have 3 questions.
Okay.
First question, this fuel tank over here on the right is just a depiction. That this fuel, just for us to make it a little bit easier to understand what's going on, right? It's not really like connected. The fuel is in the wings.
Correct. Yes, that's correct.
So this is kind of just for me to understand that it's actually this right half with this.
No. There's a little fuel reservoir. There is a fuel reservoir. Think of it like this. This thing is connected to your wings on the Cessna 172.
Okay.
Or actually, this thing is connected to the fuel selector on the floor.
Listen, I have another question.
Okay.
How is this located in space? Like so, this is bottom and the butterfly valves is up. And so is this thing located beneath the engine?
I don't know. Yes, it is. It has to be, because it has to be lower than the fuel selector.
Wait.
Did you break up? What's up,
okay.
Josh?
How's it going? Sorry.
Okay,
you missed me explaining the power plant. I'm just wrapping up the power plant.
Oh, okay. I figured it was either fuel system or power plant.
Well, we've kind of now flirted with. We went from power plant to how the gas gets into the engine.
Yeah. Okay. I was like, okay, butterfly. All right. Well.
So what did you just say? It's somewhere like close to the cylinders, right?
Yes.
Okay. And I just have a final question. So the throttle valve is connected to the throttle. And is there anything that's connected with this needle that you showed me or not? It's automatic or that's a fuel mixture?
No, that's what I explained, was the mixture is directly connected to the mixture needle. As you screw the mixture, it's actually this thing right here that doesn't look like a needle is called the mixture needle. And you are actually raising and lowering that needle with the red knob. So,
Okay.
so as you push the mixture in to go what we call full rich, that's removing the needle from, I'm going to go to green, from the, oh, that's not green. From this location down here, it's
Yes.
taking the needle out and it's allowing the gas to go in to that little line and ultimately out the discharge nozzle.
Okay. How do you like my question so far? Do you see them coming or?
I mean, I think it's relevant to what a real student is going to ask. I don't think the DPE is going to do that.
Okay, but
because
like,
they will ask where I think your like question, where is the carburetor located, is a question that the DPE would ask, because I didn't cover that. But like, yeah, no, I mean, yeah, you can keep them coming.
I mean, it's kind of fun for me, you know. It's kind of fun for me, and it's gonna be fun for you. You know, maybe Taryn is gonna ask you or someone else. We don't really get those kind of questions anymore.
Yeah, no, absolutely.
We probably ask them.
All right, so that's and just trying to get through as much of systems as possible. So I've explained the power plant system. I've flirted with the fuel system. So let's explain the rest of the fuel system here.
Okay.
So as I mentioned, the thing that's on the screen is the carburetor. This is the thing that controls how much fuel and how much air together, and the quantity of that together goes into the cylinders to then create the power. And as we talked about, the 4 strokes of power. So where is, and I don't have the screenshot anymore. So this fuel inlet on the top right.
Are we done with the engine?
We're done with the engine.
I'll give you a Julie moment. You missed something important.
Okay.
You can take a minute. Go through your notes.
No, go ahead. What did I miss?
So the engine is air cooled.
Yep.
What really important do you have to check before every flight?
So yeah, I mean, I don't know. So the air filter, it goes through a filter. Are you talking like carb heat?
No. That's why I'm giving you a Julie moment. Take your time. Take a minute. It's fine.
I don't know.
Oil.
Oh yeah. Okay. I would argue, so I've got this located, and if you look at the PTS, doesn't it have fuel, oil, and hydraulic together?
That's a good one. That would be a good comeback. I'm not sure. Maybe.
No, well, it does. So section 6 is fuel, oil, hydraulic.
So that's a good comeback. Okay.
So technically, okay, so power plant and propeller, I loosely talked about the propeller, crankshaft directly connected to the propeller in a 172 November. For the sake of brevity, because I don't want to go all night, I'm not going to talk about constant speed props, but obviously we would be prepared to explain a constant speed propeller. So I'm going to move on to just really quickly talk about the fuel system, because what I really want to talk about is the Pitot Static in gyro vacuum system. So really quickly to hit on the fuel system, and by the way, on the check ride, there's no way that the DPE is going to say, I want to go over area 3 pre-flight preparation, task Charlie, go. They're just not going to do that. I mean, you could talk about systems for 4 hours. So I am convinced that the DPE is going to say, I'd like you to talk to me about the power plant system. I'd like you to explain a constant speed propeller. How does that differ from a fixed pitch propeller? I'd like you to explain landing gear, right? So at the private level, and I'm now out of my fancy graphics here, but at the private level, in a Cessna 172 model November, what I want you to be able to understand, and the key words to use during the check ride, during your private check ride, is your fuel system is 43 gallons, of which 40 gallons are usable. So that means 3 gallons are unusable in kind of the nooks and crannies of the airplane. The fuel is stored in the wings. You've got a high wing aircraft. So each wing stores 21.5 gallons, so 43 gallons total. You've got a 4-position fuel selector on the floor of the airplane. You can either go left, right, off, or both tanks. Normal position is both, and that's just a very simple 4-way selector valve on the bottom of that fuel selector. There's no complicated machinery or electronics. You're literally moving that selector as you select it, and the valve is opening or closing. It's gravity fed, as we already talked about. So gravity is the only thing that's taking the gas from the wings down into the fuel selector and then ultimately into the carburetor, into the engine. To allow the gravity system to work, you have to have vents. In our aircraft, we've got 3 vents. Each gas cap, fuel cap, is vented, and then we've also got a vent in the, oh gosh, which wing is it? I think it's the pilot side, right?
Mm-hmm.
Okay. We've got a vent in the pilot side behind the wing strut of the Cessna that kind of blocks any crap from going into it. You do have a cross flow between the wings. So theoretically, one wing should be able to fuel the other wing and prevent imbalances. Let's see, what am I missing? You've got sumps in the lowest part of the wings and a gascolator in the lowest part of the fuel leading to the engine. Those sumps should be checked before every flight via a fuel sampler. It's a very simple valve. You jam the fuel sampler up there. It takes a sample of fuel. We're looking for any discolorations of the fuel, any water inside of the fuel, any contaminants inside of the fuel. Our aircraft uses 100 low lead fuel. We expect that to be blue in color and again, not contain any water inside of the fuel. It's important to sump again from both wings as well as from the lowest point in the engine, the gascolator.
What can we expect at the lowest point? Why is it on the lowest point?
Because the water will be down there.
So the water kind of sinks, like
the water
right?
sinks, yeah.
It's
I guess primer. So the primer so as you run through your Cessna 172 November checklist, it asks you to prime. It's on the left-hand side. As we open the primer, as we draw it back, it creates, it's like a straw almost. It creates suction, and that actual plunger fills with gas. And then as we push it, it injects the gas directly into the number 3 cylinder of the Lycoming 0320 engine. So as we prime, we're just dumping some gas into that cylinder so that when we engage the starter and it turns the propeller, or turns the crankshaft rather, the engine catches. And
where do we draw that from the primer? Is it from the wings? Like where do we suck from?
The primer is sucking from the fuel reservoir, the thing that's on the screen.
Okay. It's not from the gascolator?
I don't think so. Is it?
What is a gascolator?
Yes, in Cessna, I don't know.
The gascolator is the lowest. It's a little tiny sump inside of the engine.
Okay. Do you know, Josh?
What?
Where does primer sucks from?
The manual primer draws its fuel from the fuel strainer and injects it into the cylinder intake port.
So there you go. So it is the maybe gascolator is a Piper term. Is that not a Cessna term?
Yes, I think it's a Piper
Maybe.
term.
I've never heard of
so
gascolator.
it's fuel strainer. Sorry. So a gascolator and a fuel strainer are basically the same thing. It's the lowest reservoir of fuel. So that's the quick and dirty of the fuel system. Any questions there?
Yes. Why did you just taught me this? Why do I need to know this?
Well, because when you run out of gas, it's a really bad day. So there's several reasons. You know, as we pre-flight the airplane, it's important to note that we have a proper amount of fuel. It's important to note we have the right type of fuel. Jet fuel, for example, straw in color. Our airfield, Montgomery, has jet fuel. If they fill up our aircraft with jet fuel, it'll start, it'll run up, it'll apply full power just fine. The engine will die shortly after rotate. Probably the most inopportune time for the engine to die. So making sure we've got enough gas, making sure it's the right kind of gas, making sure the gas is not contaminated, and then, you know, arguably most importantly, it's to ensure that you understand the nature of the fuel system. And again, we haven't covered everything here, but the nature of, you know, a carbureted system is susceptible to carb ice. So if you have a rough running engine, it's important to note, like 172 Romeo Whiskey didn't 2 months ago and declared an emergency, you got to pull that carb heat on. So it's important to note that. It's important to realize that you've got the 4-tank selector and you should be on both unless you have some sort of engine issues, and then it would be wise to troubleshoot via going to one or the other. But it's important to understand the fuel system because this is ultimately what allows your plane to have power and allow the propeller to spin and not be a glider.
Okay. That's a good one. Yeah, we definitely want to know what's going on with the fuel. Can I ask you another question? You said that fuel tanks were interconnected. Why is that? Like, why wouldn't we just have like one fuel tank coming and then another? Why do we need to connect them? To cross feed them or something else?
No, it's a cross feed. So the idea is that you don't want an imbalance, one wing drawing more gas than the other, and ultimately having an imbalance in terms of weight.
And what about the vents? Why do we have like 3 of them? What do they do? Like?
So much like a straw, if I put a straw in water and then put my finger on top of the straw and take it out, the water stays in the straw. Why? Because there's no venting on my thumb side, so the water can't flow down. It can't gravity feed. So because this is a gravity feed system, if there isn't a relief of pressure on the top of the tank, the fuel will ultimately not flow down the tubes and into the fuel selector.
But can we say, like, even if it's like mechanically fed, it can also be an issue, right? Like,
sure, yeah, but this one isn't. There isn't a fuel pump in this model airplane, so I'm not bringing it up because you don't want the DPD to ask you about things that are irrelevant.
Okay, one genuine question. We have the vent on the pilot side. What's this? Just a vertical little piece. It also looks like a vent on the passenger side, on about the opposite place of the pilot side. So the pilot side is crooked like this, right? That's how vent looks like so. Mm-hmm. And what's this little metal bar like? It also looks like a vent. Is it an overflow vent or what is it? Do you guys know what I'm talking about?
I don't know what you're talking about.
Well, there is a metal, almost like a pipe. It's
on every 172 November.
Can't say, but I've seen a lot of them. And
I think the ones that I've seen are OAT gauges, because the J vent on the left side Yeah, J vent is for the fuel, and the right side is if you're talking about a short little metal
Yes.
stubby pipe with holes. I think that's
Yes.
the OAT.
It's aluminum in color. It's unpainted. Yeah, that's OAT.
So it's just a measuring tool. That's it.
Just,
All right. Yeah, it's just the outside air temperature.
Okay. It looks like a vent to me. Like that's why I said like a genuine question. I wasn't too sure.
All right, so I want to see if I can cover the 6-pack on a whiteboard in a short period of time. So let's see how this goes.
Let's do it.
Let's okay. So I should be in landscape. All right, I'm going to draw the 6-pack. Well, why can I not draw? There we go. All right. The 6-pack here. We've got our airspeed. We've got our attitude. We've got our altimeter. We've got our turn coordinator. We've got our directional gyro or our heading indicator. And we have our VSI here. So at this phase of training, you should be very, very familiar with the 6-pack. None of this should strike you as weird. Funnily enough, I've been looking for airplanes to buy right now, and I'm looking at a Mooney. It's my favorite airplane right now that I found. And they've got a standard 6-pack in terms of layout. It's not one of those what they call shotgun Moonies that has like a weird, like not enough space to fit a 6-pack. So there's enough room for 6-pack, and there are 6 instruments, but not a single one is in the normal layout. Not a single one is the normal place, funnily enough. So, all right, so let's talk.
you do a split ownership of it, or are you just going all in on it?
I'm planning to split ownership. Yeah. So
okay.
I'm looking at M20 kilos, the 231 right now.
Which one? Sorry.
M20 kilo.
Which one is that?
That's the turbo 231.
Oh, I see it. Okay.
It's they call it 231 because it supposedly trues out at 231 miles an hour. So 200 knots.
What is that?
All right, so let's talk Pitot Static. There are 3 instruments that are driven by the Pitot Static system. Those 3 instruments are the airspeed indicator up here, the altimeter right here, and the VSI right here. And when I say they're driven by the Pitot Static system, I literally mean that there is no electricity, there is no gas, no nothing. There's just air pressure in the Pitot Static system that drives these 3 instruments. Namely, so again, it's hard to know where to draw this lesson. You know, if this was like the only lesson, I'm going to draw the pitot tube. I'm going to explain the static port. I'm not going to do that for you guys. Suffice it to say, you know what a pitot tube is. You know what a static port is. I will talk about the airs though. So you've got your pitot tube on the outside of the aircraft. On the tip of that pitot tube, facing forward, is the ram air port. It's a mouth, if you will, gathering air molecules that you're shoving into it because you're flying along at 100 knots. There's also a static port that is measuring the density of the air pressure, the atmospheric air pressure. And that static port is not a mouth open to the air molecules flying at it. It's just kind of sitting, hanging out, measuring the ambient air pressure. The altimeter and the VSI only care about the static port. So, you know, if I had a bigger whiteboard, I draw, you know, the pitot tube here, and then I draw the static port. So the static port connects to these instruments. The static port also connects to airspeed, and then the pitot tube connects to airspeed. So the altimeter, the way the altimeter works is there is a series of aneroid wafers inside of the altimeter, inside of the actual instrument. If you pull it out, it's like a cylinder. And those aneroid wafers expand and contract based upon the atmospheric pressure. And the static port simply is allowing air to flow naturally into the altimeter case. Those little wafers, like if you've ever seen an old school thermometer with the little blobs of liquid that rise and fall based upon the temperature, I kind of think of aneroid wafers like that, but they are calibrated to certain pressures, and they expand and they contract if the pressure inside of the instrument is different than them. Those wafers are connected to a series of gears that directly change the hands on the altimeter. For somebody that's, you know, grown up around technology my entire life, this is a really hard concept to understand. It's really hard to imagine that there's these series of like blobs that are sitting inside of the altimeter that change in shape based upon the barometric pressure of your surroundings, and they drive a series of mechanical linkages that then change the hands on the instrument, but that's the way it works. You've got a window, as we've seen, as we've pre-flighted the airplane, and you get the altimeter 2. You've got a little window called the Colesman window on the side, and that's just dialing the current barometric pressure at the field level for where your aircraft is located. So, you know, at Montgomery, we set the altimeter setting, the pressure at field elevation, and then we take off. It goes from 450 feet to 550 feet, 650 feet, as those aneroid wafers are changing in shape and then changing the mechanical linkages that change the arms on the face. Similarly, the VSI works a very, very similar way. There's aneroid wafers inside of the VSI. Those wafers are expanding and contracting because static air, just normal air pressure of the stuff around you, is being introduced to the instrument. But there is a small calibrated leak in the diaphragm that leaks a certain known amount of air out. And so what the VSI is actually doing is it's comparing pressure change over time, essentially, via that calibrated leak. So it knows that as you know, I descend rapidly, there's aneroid wafers that are changing in size, but there's this small orifice that's allowing the air to escape, and that's what the instrument is measuring. And it's important to note that the VSI, because of all of these linkages and the aneroid wafer, and you're literally measuring this calibrated leak, the VSI lags. It's not a perfect indication. If I nose over the plane and start descending at 1,500 feet a minute, the VSI is going to take 5 to 10 seconds to catch up. It's probably my least favorite instrument of the 6-pack. Moving on to airspeed. So your airspeed indicator, probably the most important.
Like, why is your least favorite?
Because it's so inaccurate, or it's so slow to react, I should say.
Okay, you can't really rely on it, like when you really need it, like fast or what?
So as a student, students like to fixate on how fast I'm going down, and so they kind of nose over the plane, and instead of kind of looking at the attitude indicator and looking at the altimeter that reacts faster, they look at the VSI to know, am I doing 500 feet a minute? But they see it's only 100 feet a minute, and they push over further. Well, they haven't allowed it to catch up to the amount that you're actually descending. And so they end up with what we call chasing the VSI.
Okay.
And so they've got it nosed over too far, and now the needle goes to 1,000. So now they level out and they chase the condition, but VSI actually lags fairly substantially.
Okay, I understand.
So the airspeed indicator now is the first instrument in the Pitot Static system that uses ram air pressure from the pitot tube. So what the airspeed indicator is doing is somewhat simply, it's comparing the amount of air molecules being jammed into the pitot tube, into the ram air port up here, against the amount of air molecules that are just present in the atmosphere via the static port. So it's a ratiometer. It's comparing a ratio of the amount of air molecules in the pitot tube against the amount of air molecules in the static port. And that's why the airspeed indicator can only indicate indicated airspeed. And that sounds really like, oh, that's a lot of indicated. But why can't the airspeed indicator show us the true airspeed or the ground speed or something like that? Well, it can't, because it's really not measuring airspeed at all. It's measuring air molecules. And as we climb in elevation and altitude, as we know, there are far less air molecules at 10,000 feet than at 1,000 feet. So the airspeed indicator, that pitot tube, the ram airport, is the mouth is gathering less molecules. So it's telling you, hey, we're at 80 air molecules right now, versus at 1,000 feet, you might be at 100 air molecules. So that's what the airspeed indicator is indicating, is it's the ratio of the amount of air molecules that are going into the pitot tube compared to the amount of air molecules that are just sitting resident statically in the space that we're occupying. That's really kind of complex and theoretical, so we call it airspeed. And all of it's the speed that the airplane feels like it's flying at. And that's why we land at given airspeeds, like in a Cessna, our VREF speed is 60 knots. It's 60 knots indicated regardless of whether we're at sea level or at, Big Bear at 6,000 feet. Even though our true airspeed would be faster at Big Bear because the pitot tube is ingesting less air molecules. So that's the way that the airspeed indicator works. Again, it's a ratiometer. Important to note, and a DP would probably fail me if I don't talk about the airs that you can see. So that pitot tube is a small protrusion off the wing. It's very susceptible to getting ice on it. So if you're flying through the clouds, you might pick up some ice on that pitot tube. We have pitot heat to both prevent against that and melt the ice if we accumulate ice. But what happens if you get some ice on the ram airport that clogs the ram airport? Well, think about it for a second. If you've got ice on the ram airport, all that the airspeed indicator is going to do is indicate zero. There's no ratio anymore. You've got zero airspeed going into, or zero air molecules rather, going into the mouth of the pitot tube. So there's nothing to compare. You've just got static air. You would have a zero airspeed. Similarly, so if we apply pitot heat and you've got ice, it melts the ice that's sitting here at the front of the pitot tube, and some of that water then can get in the pitot tube, and we want to be able to get rid of that water. So there's a drain hole on the bottom of the pitot tube that allows that water to escape. Let's imagine for a minute that ice covers the whole pitot tube and it encloses the whole thing. So there's absolutely no air going into this system at all. what would happen to the airspeed then is you've got a bunch of trapped air. So the airspeed indicator would end up indicating, like an altimeter, as you nose over the plane and you start going down, you're probably picking up airspeed, but the airspeed indicator would actually show a descent. It would show because it functions like an altimeter, the airspeed would go down. Similarly, if you start climbing in the airplane, the static pressure that is changing, so your airspeed indicator will actually increase in nature because it functions like an altimeter, because that air is trapped. So those are some of the common errors that you see if you have some blockages in the Pitot Static system. But those three instruments are the Pitot Static system and are driven off of the Pitot Static system, both ram air and static air. Can get into alternate static, what happens if the static port clogs, you can break your VSI, stuff like that, but or turn on alternate static if your airplane is so equipped. But that's the Pitot Static system. Any questions on that? Okay. Moving right along. Oh crap. So we've then have two instruments, actually three instruments that are gyroscopic in nature. But two of those gyroscopic instruments are driven via a vacuum pump, and that's your attitude indicator and your directional gyro. So what's happening here? What's a vacuum system? Do I have a vacuum cleaner inside of the airplane? Well, no. What's happening is you have a small vacuum device inside of the airplane that is creating negative pressure, and it's actually sucking air through a system of tubes, and those system of tubes are connected to the attitude indicator and to the directional gyro. And I like to imagine that these gyroscopes, and I'm going to explain a gyroscope or a gyro in a minute here, but I like to think of those gyros as having, do you remember the boats that had the paddle wheel on the back? I like to imagine on the back of those gyros, there's like a paddle wheel on them. And so as you are creating negative pressure in the vacuum system, it's sucking air through the paddle wheel, and the paddle wheel is spinning the gyro very, very quickly. So it's important to note that the vacuum system is connected to the engine. It does not require any electricity to function. The vacuum system is independent of the electrical system. It's independent of the Pitot Static system. It's literally driving just these two instruments. So if your Pitot Static system clogs, it's not going to affect the vacuum system. If your battery dies, it's not going to affect the vacuum system. The vacuum is completely powered by the engine system. So you've got the vacuum that's drawing the air out, spinning the paddle wheels, spinning the gyros. So what is a gyroscope? What do I mean by that? Imagine if you've ever played with a gyroscope, and here this is really hard to explain without being in front of you guys and having a gyro or having at least a spinning plate. But imagine on my pencil here, I had like a mini bicycle wheel, right? And that mini bicycle wheel spun on my pencil, and I could spin it real fast. Well, that vacuum system is sucking air through a little paddle wheel connected to the plate or to the bicycle wheel, and that spins the bicycle wheel very, very fast. As we spin the gyro or the wheel, there's an important principle of a gyro that you need to understand. So imagine I've got a spinning wheel on this pencil. If it's spinning fast, it's very difficult for me to move this pencil like this. Very difficult. And that's because of a principle called rigidity and space. So a gyro that's spinning is very resistant to me moving it. So what's happening is in the attitude indicator here, I keep wanting to draw on this screen, but I'm actually down here. There is a gyroscope that is spinning horizontally. So it's spinning inside of the attitude indicator horizontally, just like what I just drew. So that gyroscope, that gyro, is resistant to motion as our airplane banks left and right. That gyro wants to maintain level with the horizon. That gyro is level with the ground, sort of. So as your airplane moves, your airplane is actually moving around that spinning gyro in space, and that spinning gyro is resistant to wanting to move left and right with the airplane. So that gyro is connected to the mini airplane that you see on the attitude indicator. So all that's happening as you bank left and right is the instrument is moving around the spinning platter or the spinning disc connected to the miniature airplane. And so you see the artificial horizon moving around that airplane. Similarly, just like left and right bank, if you pitch, that gyro wants to maintain level to the ground, so you end up moving the instrument up and down, or pitching it forward and backwards relative to that thing spinning inside of there. So it would be just like if I took my bike tire off of my bike and I had you hold both sides of the hub on like the quick release skewer, and I spun it real fast and you were sitting here holding it, you would have a difficult time doing this because of the principle of rigidity and space. So all the vacuum instrument is doing is it's spinning that disc inside of the instrument, and the instrument and the airplane as a whole ends up moving around that disc. Does that make sense? Very hard to explain without us physically being together.
Yes, actually it does. I wouldn't be able to explain this remotely. Half.
So now, if you understand that, the directional gyro is much easier to understand. So the directional gyro, rather than having a horizontal gyro, it's got a vertical gyro inside of it, spinning via the vacuum system, pretty much the same way, but it happens to be vertical in space. Just like if I was holding the skewers of a bicycle and spun it, I would have a really hard time doing this. So what happens is, as the airplane moves around in circles, that spinning disc is resistant to changing its orientation. So via a series of linkages, some gears, it moves the heading indicator. Essentially, the plane moves around that spinning disc via, again, a series of linkages. I could show a picture and it would make a lot more sense, but it's important to recognize that all that's happening is your spinning disc is oriented in one direction. Let's say it's oriented west and east, and then the aircraft moves around that gyro that is resistant to motion. And that's what gives you the heading indicator. And so that's why we have to set the directional gyro to the magnetic compass. The directional gyro has no idea which way north is, which way south is. You could set the directional gyro to north, and all that's doing is that spinning disc is inside of there, and as you move about all the other cardinal directions, that spinning disc continues to be oriented north and south. if that makes sense. So it's the same principle as the attitude indicator, only instead of the disc spinning horizontally, it's spinning vertically, and the instrument moves about that spinning disc. Rigidity and space is the important principle here. Does that make sense?
Yes.
Yeah, nicely explained.
Cool. And then I guess that leaves the turn coordinator. So if we've got the Pitot Static system powering the altimeter, VSI, and airspeed, and we've got the vacuum system powering the attitude indicator and the directional gyro, what's powering the turn coordinator? Well, what's powering the turn coordinator is the electrical system. And this is really intelligent in design because vacuum systems fail and fail often. You know, when I started flying, the vacuum system was really hard to wrap my head around. I was like, wait a minute, there's a vacuum inside of my airplane. That doesn't make any sense. Why would that be? Well, when you understand that there's this gyro inside of there, how else using the engine system alone are you going to spin this disc fast enough to really have it rigid in space? Well, you've got to come up with another system. So it's literally a little tiny motor creating suction, sucking air through it. So what the turn coordinator does is the turn coordinator has a gyro in it as well that's actually canted 30 degrees. And that gyro—
What does it mean, canted?
Canted means it's offset, it's beveled, it's again, this is really hard to explain if I'm not here with you guys. So instead of being up or down or left or right, it's actually oriented back to front 30 degrees like this, if that makes sense. So it's a spinning disc that's not flat, it's from front to back 30 degrees diagonal, if that makes sense. I'm pretty sure it's 30 degrees. I'm completely going from memory at this point. So that spinning disc is electronically driven. So it's a little electric motor that's spinning that disc that is running from the electrical system. We're not going to get into the electrical system tonight. Suffice it to say, there's a battery, there's an alternator, there's something that's supplying 24 volts. And that voltage is going into a little motor that's spinning a gyro. It's still a spinning plate inside of the instrument. But the instrument has a bit of a ratiometer inside of it that via, and this is where I'm going to explain this terribly because I've never been good at explaining the rate of turn indicator, but via a principle of gyroscopes called gyroscopic precession and rigidity and space together, the turn coordinator via that miniature airplane and these indications over here, when your airplane wing lines up with these indications, you know that your rate of turn is a perfect 3 degrees per second. Regardless of bank angle, regardless of speed that you're going through the air, your turn coordinator indicates via that spinning gyro that's electronically driven, it indicates that the rate of your turn is 3 degrees per second or 2 minutes all the way around. At the bottom of the turn coordinator is the slip skid indicator with just a ball inside of the vial of kerosene, most are, that just shows you the coordination of your turn, or whether there's centrifugal force that's drawing to one side of the turn or other, whether you're slipping or skidding, whether the rate of turn matches the bank of turn, whether your tail is moving at the same speed as the wings. So that's what the turn coordinator does. The slip skid indicator, the ball, there's nothing powering it. It's literally just a ball, a weighted ball, sitting inside of a vial of liquid kerosene that moves back and forth depending upon the centrifugal force, the forces exerted on that ball. The turn coordinator portion, the rate of turn portion, is powered again via electronic gyros. So that's the turn coordinator system, which again, if your vacuum fails, you lose your attitude indicator. Your turn coordinator is giving you a lot of the same indication. It's not giving you any pitch, but you can get pitch from airspeed, altitude, and VSI, but it is giving you, it continues to spin because it's electronic. It's giving you bank indication. So your attitude indicator might fail, you're in the clouds, but you've still got your bank indication from your turn coordinator. You know when your wings are level. So really quite ingenious, redundant system here. Any questions on the 6-pack? And actually, I guess my question would be, can you guys explain the turn coordinator better than me?
Okay, the first answer
Actually,
is
not
no.
until you, I mean, I don't come to think of it. I never thought of it until now, but I don't even think I've ever had it explained to me other than it's electrical and, you know, that's it. And then I realize now I've never even had to explain how the turn coordinator works. So I'm like looking all over this POH trying to figure out like where I'm going to read up more on it, because I don't know how I got this far without ever having to explain it.
It's really hard to explain. So it operates on principles of gyroscopic precession, knowing that you know, when you exert a force against a spinning disc, that force is felt 90 degrees in the direction of the spin, but it also is rigidity and space. The canting of 30 degrees is why it can indicate both bank and rate at the same time, but I can't articulate why.
Yeah.
But I have I think you just missed something. Other than the redundancy, what's the point of this instrument? Why is it important, 3 degrees? It just standardized or what? Is it important for us as a student pilots?
Sure. I mean, the inclinometer indicates the quality of the turn. So your slip skid indicator, that ball needs to be centered. It's your really your only indication instrument wise of your yaw condition, of your coordinated condition.
Ah, I see. Okay, because I got an impression just as like a backup, and I know it does like 3 degrees, but it doesn't really mean much to me. 3, 5, 1.
Yeah, so it's important for that ball to be centered. If it's not centered, again, that's what I was trying to explain with the tail moving too fast or too slow for the rate, for the bank angle that you're in the turn. So in different lessons, we would have covered adverse yaw. We would have covered, you know, the nature of aerodynamics in a turn. But this is your indication of a slip or a skid. Again, the idea that one of your butt cheeks is feeling more pressure on it than the other. Ideally, as your plane is banked in a turn, you should have equal pressure on the outside of that turn.
I see. Okay, I think it's for another lesson, but it definitely helps us become better pilots.
Yep.
If we keep an eye on that instrument, right? And is the turn coordinator, you know, there is a rigidity in space and there is a precession, but you only mentioned precession in the turn coordinator. Doesn't it apply also to, I'm gonna sneeze.
So I know your question. So does the attitude indicator or directional gyro operate on the principle, on the gyroscopic principle of precession? No, but precession is important to realize because you have to, the reason on your checklist you always have the DG to compass or HI to compass is because your directional gyro will end up precessing about 15 degrees 15 degrees every 15 minutes, right? So you've got to be constantly matching your directional gyro to your compass because it's precessing.
Ah, okay, so it's kind of like a safety thing as well. It's
Correct.
Not just like purely physics.
Correct.
Ah, okay. Well, can I give an input?
Sure.
Great as always. You know, I think we're kind of like getting used to it by now, Josh. Maybe we should kind of like secretly start recording him and then tease like Jason Shepard, like 5 years from now, doesn't matter. Okay. Okay, yeah. I mean, definitely, especially, okay, let me start from the beginning. Engine, you know, Josh wasn't there. A really good explanation what engine was. You know, the principles of internal combustion engine, 4 strokes, it's mandatory. You did, I wouldn't go more than that. So you had the valves, you had the crankshaft, you had, you know, the connecting rod. That's pretty much it. You know, maybe less, certainly no more than that. Because if you notice, I ask you like, so basically what they're doing is every cylinder is doing something else and they go bam, 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 bam. And that's it. So yeah, you know, that was a good explanation. I was kind of like putting myself into a mindset of someone who doesn't know what like rods are and crashes and valves. So you had me on a private pilot level at 100%, but you did not exceed my imaginary capabilities. So just be careful not to go more than that.
Yeah.
I would say that was the max. Valve, connecting, okay, you know, I was like, okay, I get it. But like anything else, I think it would be like overdoing it for a pilot. But like for me, I was like at 100, but I was able to keep up. So yes.
Well, I think, you know, what I think matters is how the DPE will introduce this element. So if they say, I want a lesson on the power plant, well, then it's kind of what I did. If it's, I would like you to explain to me a lesson on 3 systems, Pitot Static, vacuum, and the power plant, well, then it's, you know, horizontally opposed, naturally aspirate, you know, it becomes the bullet points of 4 strokes, suck, bang, suck, squeeze, bang, blow, you know, it becomes a lot higher level. Yes. So that's where it's really important to gauge the DPE as the student. What do you understand about how a combustion engine works? Do you understand power? No? Okay, let's explain it. No? And so, and I think that's the real life too. Like, you know, I'm not gonna sit down with a student and start explaining the 4 strokes of a 4-stroke combustion engine to somebody that's been, you know, wrenching on cars their whole life.
Yeah.
Yes. Okay. Yeah. So that was pretty good. Fuel system, really good. Why? You know, like why? Yeah, we want to be safe. We want to. I would, I would end up like every like part in one sentence. So why do we know the engine? Obviously, you know, we need to know how it works, but also we need to know like how everything works because we want to be able to troubleshoot. So as I mentioned before, you know, we do have that Venturi valve. It does can cause that kind of roughness. So it's not strictly mechanical. You're not going to go into like mechanic school, but now that you do know how an engine works, now you actually know a background. You know, one day if you feel sentence kind of like a conclusion, okay, so like now you get it, like, because I was thinking about like what someone said, and maybe it was like why, you know, like why safety. We're not gonna know how to repair it, but with all these kind of systems, I feel that you're a much safer student pilot than you were, because not only you know how they work, but you also know the background of it. So I would kind of like just wrap it in a nice little like a present, and be like, okay, you know what? Like I know you're not gonna fix an engine, but now that you know, you're much safer now. Like, would you agree? And if I were an examiner, I would be like, yeah, I completely agree.
Yeah.
Kind of like for like kind of like just a wrap up, and instruments were really good. You know, instruments were awesome. Really hard to explain. I would probably like screw myself over like 10 times over by now by like saying something. You know, I think you just kept it You did mention the wafers, you did mention the pitot, you did mention the ram air, you did mention everything you were supposed to mention in an understandable way without actually screwing yourself over by overemphasizing some kind of details of you know, biometric scale. You did mention the leak. So it was like really up to the like PTS. I was really following you. But you did it in a way that you kind of like wrapped it up in, I didn't time you, I wish I did, but it was really like to the point. I would say 15 minutes, 20. I'm not sure, Josh, if you follow. So I'm like really impressed with how you handle the instruments. Everything is there, everything is covered, but without all kind of mumbo jumbo technical stuff, you know, like pitot heat switch, heater, 100 watts, ram air, this and that. So yeah, I can't really add anything, especially because you were able to like explain gyro strictly using, you know, basically a few drawings and a really solid explanation. I'm actually, I'll tell you guys right now, I'm gonna have a maybe a little gyro or a little toy. Because I'm not sure if I can be eloquent as you. So I'm just
I think having a gyro is super beneficial to the lesson.
Yeah. If nothing else, like even a fidget spinner or something.
Yeah, a fidget spinner would be perfect, actually.
Yeah. Yeah. Yeah, my feedback, man, I hope this was helpful for you teaching it, because I don't really have a lot of negative feedback. I mean, I thought that was pretty solid. And honestly, like, I'm not just trying to ingratiate you, but all the times that I've learned these instruments, I'm thinking back to it, a lot of my instructors, I think they copped out and they just showed videos, you know, because it's just easier when you got the visuals and you got this fancy computer diagrams. So honestly, that was probably one of the best oral or audible descriptions of those instruments without having visuals to go off of, that I could understand, even trying to put myself in the shoes of not knowing too much. I think honestly the only negative feedback I would have, or and I'm sure that it would be different if you were teaching it to somebody and drawing out the fuel system, but just being able to relate the location of the different parts of the fuel system, being able to say, the fuel selector is kind of the highest part. So where are you going to go first? If you need to shut off your fuel, you're going to go to the fuel selector first. And just being able to, I guess, spatially articulate where the different parts of it are. But I mean, I'm sure if you were drawing it out, that would just come naturally when teaching it.
That's a great point.
That's literally the only thing I wrote down on the sticky note, though. That was solid. So I hope it was still helpful teaching.
No,
I know that you didn't get a lot of feedback here.
No, it is. It's super. I mean, it's helpful to teach to anybody. Honestly, it's more helpful when they know what you're talking about and can call you out on bullshit. But yeah, cool.
Definitely.
Yeah.
Like, I really don't have much of the feedback itself. Maybe the main feedback, other than like, because it was really like, like I can't really say it. I have a feeling it's better than I would do. But maybe that kind of feedback, like, okay, so why is this important? I want you to be a safer pilot. I want you to be a safer pilot. Why do we do everything we do? Because I want you to be a safer pilot. And I like maybe say that a few times, like, what's the point of the lesson? Are you going to fix an engine? No, but now you're a safer pilot.
Yeah.
I would just, maybe my main feedback, everything else, like I don't really have a feedback. I had one instructor that had used broken down instruments, altimeter, and
that would be super nice.
That was cool. Like, they were dirty as hell, like, and whatnot. But that was pretty cool. Actually, that really helped me. He didn't have an intersection, but I did actually saw those little wafers. So wafers. So that was pretty cool. I wish I had one. Josh, why did you steal one from your school or something?
I know, right?
On the black market.
When you did the engine, the power plant part, did you draw it out or did you use a picture?
I used a picture. That'd be really hard to draw, I think.
Yeah, because I was freaking out. Like I've been freaking out on how I would draw a lot of this stuff out, and so I was like, okay, I wonder if he used a photo.
No, I used a I could share what I used. It was just a picture of 4 cylinders. Let me.
Yes. Would you think Chase, that the carburetor, like, could you do a little less on the carburetor, or would you say that it was pretty much it?
I mean, I would. So again, you have to kind of. There's no way that the DPE is going to say, I'd like you to explain like the power plant without giving you any more guidance. Because like, where do you stop? Well, you can explain the engine, but where's the engine get its gas? Okay, well, let me explain the carburetor. Okay, let me explain the fuel system. Okay, well, how does the whole thing start? I mean, okay, let me explain, the electrical system and the starter. Yeah, so you're going to get guidance. I don't know if the carburetor is part of the fuel system, part of the power plant. I don't know.
Yeah, no, that was pretty cool. Actually, I kind of refreshed myself as well, because it's been a while since I get into the details. So I personally enjoyed it.
Just keep in mind that you got to be able to explain a constant speed prop, landing gear, hydraulic. I just as a pet peeve, I love the, you get in, test my brakes. Would you like to test your brakes? Yeah, I like to test. Like, what's the point of testing the right side brakes? You've only got 2 master cylinders.
Yeah.
And they're both, So, but yeah, I don't know. That's how I'm going to treat systems.
Nice.
Yeah.
Nice. Yeah, I don't like, maybe we are kind of like, maybe Josh, we need to like, think of something to criticize Chase a little bit more. Like, I don't think we are like a good audience because we are not pushing him.
No, this is good. I mean, it's like I said, it's good to just kind of try to explain this stuff.